Because I just didn't pay attention that there is Easter Sunday, and
Okay.
yes,
I saw that too.
yeah, I'm so sorry, my fault. So I'm glad you pointed out to me. So we're gonna move it. If we need to review, I don't want you to think that I'm not gonna review. If you need to review before the test on that Wednesday, not Wednesday, Thursday or Wednesday, I invite everyone to both sessions anyway.
Okay, cool.
We can continue reviewing. Okay, so we'll give you some time to finish up everything else. Okay, any questions for me? Any questions? Okay, chapter 4. Chapter 4 is not going to be on this test, of course. This is chapter 4 will be tested on test 3. Okay, so remember in chapter 2 we talked about limits. Remember to stop me anytime, okay? In chapter 3 we talked about derivatives and differentiation rules. Well, now in chapter 4 we are going to look at applications of differentiation. And we have 3 major applications here. We're going to look at graphing. We are going to look at optimization. And finally, we're going to look at Newton's method. These are the major applications that we are going to look at, and some minor things here and there in between. And the last chapter will be chapter 5, and we'll talk about that hopefully soon. Okay.
This class is being recorded right now, right?
Yes, I did start recording. Yes.
Thank you.
Yes, I see. Yes, thank you for every now and then remind me to look to make sure that it's working. Yes, it is. I'm working on 3 computers to hopefully get this done right. Okay, so applications of differentiation. The first application we're going to look at is 4.1, in which we are going to talk about max, min. Okay, so we do have 2 different groups of max, local, also called relative, interchangeables, maybe the same thing, or global, absolute. You can call local and then absolute, or global and relative, it doesn't matter. And the same thing for minimum, same. Local and global, or absolute. So let me just give you a couple of examples. What is local? What is global? What's the difference between the 2 of them? So let's suppose, and we're going to look at the graph in a minute. This is just a simple situation. Let's say we have a graph that looks like this. Obviously, this point is not absolute because there is a higher value than it for this function. But the function exists on both sides, and function values are smaller than this one in this open interval. This is called a local max. Identical with this, that situation is also this. It is a local min because I can show the open interval where both sides of that point where function values are bigger than this one. It happens that this point is also an absolute minimum because there is no other y value smaller than it. Okay, now let's go back to these two endpoints. This cannot be local because the function does not exist on this side. No local ever at the endpoints. But can it be an absolute? No, because this value is not the minimum of the function, is not the maximum of the function. So this point is nothing. What about this one? Can it be local? No local, because it's at the endpoint of the interval. And I cannot show the open interval both sides. Can it be absolute? Yes, it is also absolute in this case, because it's an absolute max. Why? Because there is no other function value higher than this one. And now I would like to look at a graph in your book. And since you'll tell me if you can see, I can put the book on another book. It's very heavy. I won't be able to hold it for too long up in the air though. I need to exercise more, lift weights more. Okay, so let's choose any, can you see? I'm looking at, this is page 280, and I'm looking at any problem you would like to pick so we can analyze local max, local min, any problem.
Can we do maybe number 3 first?
Number 3 first, very good. So can you see, or should I put the book on another book to raise it?
The text is kind of hard to see, but the graph you can see.
Okay, let me bring another book. And this is something I recommend to all of you. Excellent book. Excellent. Okay, so I'm gonna try to do this. Is this better?
Yes.
Thank you. Okay, so we start with number 3. And we see that this point is nothing. It's not local because it's at the endpoint of the interval. It's not absolute of anything. It's not absolute max or absolute min. This point, I can show the open interval. So this is a definitely local minimum. Is it absolute? No. It's not absolute because there is a lower value than it. What about this? I can show the open interval. It's not, it's local max. It's not absolute because there is a higher value than it. We finally get to this. It's a local. I can show the open interval. And also it happens to be the absolute minimum. And finally this, is it local? Never at the endpoint of the interval. But it happens that is the highest point for this function. Therefore, this is an absolute max. Any questions so far? Okay, do we need to choose another or we move on?
We can probably move on.
Okay, very good. I'm looking on page 281, and I would like to pick a problem from there, let's say 32. We're going to talk, before I even copy the problem, we're going to talk about what it's called a critical number. of a function. Why critical numbers are important? Note, only critical numbers can not necessarily turn into max-min of a function. If a function has no critical numbers, the function does not have a max-min. Once I determine the critical number, do I know whether it's a max or a min? No, I have no idea. More work needs to be done before we conclude whether it's a max or a min. But only critical numbers can turn or may turn into max-min of a function. No critical numbers, no max-min. Okay. Critical numbers come from two sources. From f prime of x being 0, when the derivative is 0, or from f prime of x being undefined at x values where the function exists. The function is defined. If a function is not defined at a point, if its derivative is not defined, that cannot be a max or a min. So a function can have critical numbers coming from both sources. Critical numbers coming from f prime being 0, and it can also have critical numbers coming from f prime being undefined, where the function is defined. So now I'm copying the problem from 32, the function from 32, and let's see what we're asked to do. Well, obviously we're asked to find the critical numbers. So we are given f of x equals 2x cubed plus x squared plus 2x. Question again, find critical numbers. So this is 32 on to 81. Since critical numbers come from the derivative either being 0 or undefined, then I have to start by finding the derivative. So then f prime is 6x squared plus 2x plus 2. Is this okay so far? So we know that there are two possibilities. Either f prime of x is 0 or f prime of x is undefined. We always have to check both. Well, there is no way a polynomial function is undefined, so there are no critical numbers coming from this. But we have to solve the equation 6x squared plus 2x plus 2 equals 0 and see if critical numbers come from f prime being 0. I will definitely divide by 2, so I get 3x squared plus x plus 1 equals 0. I will use the quadratic formula. Negative b plus or minus b squared minus 4ac over 2a. No critical numbers whatsoever. This is not real. So therefore, this function has no max-min. Good. Let's continue with a rational function this time. Please pick, if you'd like, problems 29 through 44. Till you choose one, I will choose a rational, 35. So we are given g of y equals y minus 1 over y squared minus y plus 1. Okay. On the previous problem, I did not ask you about the domain because we know the domain of a polynomial function is all real numbers. But here, I do have to look at the domain. And the reason is this. If I find that the first derivative is undefined, then I have to go back and check whether the function is defined at those points, or x values. So in this situation, I would definitely start with the domain of the function. Here, I didn't really need to because this function is defined everywhere. Its derivative is defined everywhere, so there is no problem. But for rationals, I have to, oops, I took my problem away. So when you set y squared minus y plus 1 not equal to 0, you will realize that this has imaginary solutions, and this will always happen. Always true. Why? So y equals negative b plus or minus b squared minus 4ac over 2a. Not real. Therefore, this is never 0. So it happens that for this function, the domain is also all real numbers. Okay. So potentially critical numbers can come from g prime being 0. Well, we know it's not going to happen because when I differentiate this, I will have only this in the denominator squared. So I already know critical numbers will not come from g prime being undefined. But I have to find g prime. Watch me run out of room. Quotient rule. We have to remember we differentiate the numerator. When I differentiate the numerator, I get 1 times the denominator. So then I write y squared minus y plus 1 minus, I may not run out of room, the numerator for once, 2y minus 1. Let me stop for a moment and give you a second to ask questions. Any questions, or are we okay? Okay then. This is why in the previous chapter we wanted to simplify this to the fullest. We need it right now. So y squared minus y plus 1, 2y times y with minus in front. 2y times negative 1 is negative 2y but with minus in front. Negative 1 times y with minus in front. Negative 1 times negative 1 is 1 with minus in front. Okay, I'm checking my work. Yes, that's minus, it's plus, that's minus, it's plus, and that 3 negatives. Okay, let's see if we can simplify anything. I left my phone on. I just want you to know if just in case one of your colleagues calls. Okay, so I have a negative y with a positive y. I have a positive 1 with a negative 1. And then I have a negative y squared and plus 2y over y squared minus y plus 1 squared. And this is the reason why I insisted, not that I would deduct points, but I insisted for you to completely factor this. It makes our life so much easier now because we have to look at this equation and we have to write the solutions. So the more I work on this, the better simplified it is, or the fullest, if I can, as it is right now, the easier it is to continue. So I factored out negative y, and I got y minus 2. Negative y times y is this, negative y times negative 2 is that. Can you follow, everyone? Anything? Please stop me if you have questions. Anyone? Okay. So obviously we have a y equals 0 and a y equals 2. And these are the critical numbers of the function. Also, I already mentioned this is not going to be the case. This, first of all, doesn't have solutions, real solutions. And that's why the domain is all real numbers. And where this is defined all the time, and the function is defined all the time, and therefore there are no critical numbers coming from G prime being undefined. For this particular problem, I would like us to take it one step further. We are not asked to do this now, but I would like to determine, in anticipation of the next sections, I would like to determine, okay, these are critical numbers. Do they turn into max min? I'd like to know. If they do, I would like to know what they turn into. Okay, so I highly recommend the following table. We've been using this table. If you don't like this table, use your own. But please summarize the information somehow. So we have the domain, negative infinity to infinity. I prefer putting the derivative first, and you will see why. And the function next. All I'm interested in is right now putting in the 0 and the 2, where the first derivative is 0. I would immediately, where is my calculator? Here it is. Okay. In the graphing calculator, I will just need to plug in. I don't really need calculator, sorry. So 0, 0, 0, so this is negative 1. And for 2, the numerator is 1. 4 minus 2 is 2. 2 plus 1 is 3. I don't need any calculator for that. One more time. 2 minus 1 is 1. 4 minus 2 is 2. 2 plus 1 is 3, 1/3. That's it. That's all I needed. Okay. Now let's take a look at the derivative. Again, I'm going to copy it here. I don't want to write over there. Minus in front. Okay. So first of all, I would like to study the sign of this derivative, of this function. When I study the sign of this function, since this piece is always positive, I don't care for it. It's always positive. I'm not going to plug in any numbers in that piece. I know that this function is quadratic, right? Is negative y squared plus 2y. It definitely has a maximum. I know it crosses at 0 and 2. So the sign, the sequence of signs must be this. Negative here, positive here, negative here. If you say, I don't want to do this, I like to plug in a number. Plug in a number. So plug in this quantity, not in this. There is no need to plug in here anything. Just to study the sign, right? So if you plug in negative 10, this becomes positive. And negative 10 minus 2 will be negative, exactly as expected. In the middle will be positive. You plug in 1, you will see the derivative is positive, and if you plug in 10, the derivative becomes negative. Okay, so now let's analyze what is happening here. When the derivative is negative, the slope is negative. The slope of the tangent line to the graph. That's what it means. The derivative is the slope of the tangent line to the graph. So if the function has to do this for its derivative to be negative, what does a function like that do on the portion on which its derivative is negative? What does it do? It
decreases.
Thank you. What does the function do when the first derivative is positive? What does it do for the derivative for the slope of the tangent line to be positive?
Increases.
Very good. This is what we call the first derivative test. Meaning, if the derivative changes sign to negative, from negative to positive, what kind of point will this be? It decreases to a certain point where the derivative is 0 or undefined, and then it increases. What type of point will be 0, comma, -1? What will this one be? So I'm going to write here local min. 0, comma, -1, local min. What about 2, comma, 1/3? So 2, comma, 1/3 will be, since the derivative changes sign, it's positive first, is 0, and then negative. Obviously, 2, comma, 1/3 gives a local max. What happens when the derivative does this or does this? I still have a critical number in the middle, maybe coming from undefined or coming from f prime being 0. If the derivative does not change sign, these points cannot be, even if the function has a critical number here, or it's, or the coming from f prime being 0 or undefined, if the derivative does not change sign, this is a critical number, but it's not a max, local max or local min. Also, you already told me here, when the derivative is negative, the function is decreasing. When the derivative has a positive sign, the function is increasing. So note, the first derivative positive, function increasing. The first derivative negative, function decreasing. So then I go back and I just write here local max. So in this particular case, in this problem, we found two critical numbers. It turned out that both are points of maxima. The first one is a local min, and the second one is a local max. Any questions for me so far? Any questions? Any questions? Can anyone get in touch with Omari? Mason, can you get in touch with Omari for me, or I will?
Yeah, I can text him. He just never responded to our
I know.
to our group chat. So
yeah, I know. I'm worried about him. Okay. And what happened to?
I wasn't sure if he was in the Monday, Wednesday class.
No. What happened to Colby?
I honestly not sure who that would be.
Okay, I'll have to get in touch with both of them. Okay, any questions on how to determine critical numbers? Would you like to choose another problem, or we continue with something else?